this thing has the units of the flux because it's K times temperature difference divided by length, because lambda has the inverse length units. And this is unitless, and you're multiplying the fluxes with the area, so that's the units for the heat, not the heat flux, but the heat per unit time. So that looks correct. And okay, so we found out the temperature profile in the fin for the case where the fin end is insulated. We actually came up with a way to derive the amount of heat lost, and we said that you can actually find out this in two ways. I think it might be a good exercise for you, so I recommend you to do this as a homework, not to be collected, not to be handed in. Okay. And this is going to be a good validation of this thing as well, so you can actually compare it with this finding that we found in the class. Now, let's talk about something called the fin efficiency for this case. Okay. Fin efficiency. Fin efficiency we denote as eta F, and it means the amount of heat transferred, or the actual heat dissipation, divided by heat dissipation in the most ideal case if the entire fin surface is at the T wall. We know that the fin will have a smaller temperature than the T wall, and we know that just because it's having a smaller temperature, the heat transferred through the surface is going to be less than what it would be if it were at T wall. So imagine that you have this fin, right? I imagine that this is like 350. This is 300 Kelvin, the air. And if it were all like 350 Kelvin everywhere, as opposed to having smaller temperatures, 350 here, and then 320, and then 310, then since the temperature difference between the air and the fin would be smaller in this case, as opposed to this 50 Kelvin difference, you would get a smaller, so here you would get larger heat loss. You would get a small heat loss here, right? So the most ideal case would be the fin, the conductivity, the conduction in the fin is so large that basically, so large that the entire fin is at almost the same temperature as the wall. Okay, it would be the most ideal case, and the deviation from this ideality is just the efficiency. Okay, if you're close to the ideal, you get 100% efficiency. If you're away from the ideal, you have smaller than 100% efficiency. Okay, let's calculate it for the let's calculate the fin efficiency with the parameters given. Okay, now so the eta F is equal to The actual heat dissipation is what we found here already, lambda K T wall minus Tf times BW tangent hyperbolic lambda L divided by the heat dissipation if the entire fin surface is at T wall would be the heat transfer coefficient H times the area, which is the B plus W times 2, which is the perimeter, times L, the length, times the temperature difference, T wall minus T fluid. And T wall minus T fluid would cancel, right? And we should actually remind ourselves of the value of the lambda, right? Lambda square. What was lambda square? Let's check. We define it to be 2h over k w plus b over ew. 2h k b plus w plus divided by bw. Right? Good. So instead of this term, so basically, yeah, let me use green. Look at this number, please. Look at this quantity. It's basically h b plus w2, which is this numerator. And in the denominator, kbw, right? You have it in the denominator here. Basically, so this one must be 1 over lambda squared. And after the simplification, you get lambda tangent hyperbolic, lambda L, divided by lambda squared L, right? And after you simplify the lambda and lambda squared, you get tangent hyperbolic lambda L over lambda L. A very simple expression, right? So the fin efficiency is so if you know the conditions like H, K, and the dimensions of this system, you can easily calculate the fin efficiency. Tangent hyperbolic is a function that you already know. And if you plug in the lambda and L, you would get the fin efficiency. And if you have the fin efficiency, you can calculate the actual heat dissipation from the perfect case. You can just assume that the heat transfer, I mean, the entire fin is at a constant temperature. So it's very easy to actually calculate the heat dissipation if the fin were at a constant temperature long, which was actually TW. Okay. So that was case 1. Any questions so far? If you don't have any questions, let's do a case 2. Okay. And the case that we're going to study this time the fin edge is not going to be at is not going to be perfectly insulated. But we're going to have an infinitely long fin. Well, actually, I didn't need to like extend this, but just exaggerate it schematically. L goes to infinity. Extremely, or let's say infinitely long fin. Okay. And yeah, the other conditions are the same. You have the B, W, and so on. So what are going to be our boundary conditions then this time? The boundary condition 1 is at x is equal to 0, t is equal to t wall, or in other words, psi is equal to 0, theta is equal to 1. And our boundary condition 2 is going to be at x is equal to L, right? This time, the fin is so long that like all the heat transfer occurred, and there's not going to be any more heat transfer. So, which means that the tip of the fin already came to the temperature of the fluid. So basically, T becomes equal to the fluid temperature. So it's too long. It's so long that the tip of the fin is the same temperature at the as the air. Okay, so this means that psi is equal to 1, theta is equal to Tf minus Tf divided by Tw minus Tf, which is 0. Okay, so let's solve our equations. So now our theta is equal to C1 sine hyperbolic lambda L psi plus C2 cosine hyperbolic lambda L psi. And from the first boundary condition, we have 1 is equal to C2, right? Because the let's do it. C1 sine hyperbolic 0 plus C2 cosine hyperbolic 0. From here, this is 0, this is 1, C2 is 1. Okay. The second boundary condition gives us that theta is equal to 0 when psi is equal to 1. Right? Okay. And this was 1 already found. And you have 0 is equal to C1 sine hyperbolic lambda L plus cosine hyperbolic lambda L. And you have C1 is equal to minus cosine hyperbolic lambda L divided by sine hyperbolic lambda L. And what do we call this? The cosine hyperbolic divided by sine hyperbolic. Does anybody know?
Cotangent hyperbolic?
Cotangent hyperbolic lambda L, right? Or inverse tangent hyperbolic, or sorry, not inverse, but 1 over tangent hyperbolic lambda L. Okay, good. And can we calculate the fin efficiency and the heat loss and like all these quantities? Yes, we can. The Q lost is equal to, that's again the Q at X x is equal to 0 times BW, right? And that's equal to minus k dt over dx at x is equal to 0 BW. And from our previous calculations, we found that dt over dx is tw minus tf over L d theta over d psi, right? T d theta over d psi minus k b w t w minus tf divided by L d theta over d psi when psi is equal to 0. And let's write it here. D theta over d psi when psi is equal to 0 is C1 lambda L cosine hyperbolic lambda L psi plus C2 lambda L sine hyperbolic lambda L psi we just get C1 lambda L, which is basically minus cotangent hyperbolic lambda L times lambda L, right, from here. And we plug it in here. K B W T wall minus TF over L cotangent hyperbolic lambda L lambda L. L's cancel. From here we get Q lost is equal to K B W lambda T wall minus TF cotangent hyperbolic lambda L. Yeah, that's the amount of heat lost for the case of infinitely long fin. Okay. So can we calculate the heat efficiency? Sorry, fin efficiency. Fin efficiency. Which is equal to this kBW lambda T wall minus TF cotangent hyperbolic lambda L divided by the heat loss hypothetical or theoretical heat loss if the entire fin were at T wall, right? So that's going to be H times T wall minus TF times the total area, which is the perimeter, times the L, 2 times B plus W times L, correct? And from the previous notes, where's my, yeah, lambda square is 2h over k, B plus W, plus W over k BW, right? So let's pinpoint where is the lambda square in this expression. K BW 2H. Okay. So there you go. Okay. So this part is 1 over lambda squared from this. Okay. And then the fin efficiency comes out to be lambda. And yeah, why don't we cancel the TW minus TFs? Oops. Okay, good. So we have lambda cotangent hyperbolic, lambda L, divided by lambda squared L. And after simplifications, eta F comes out to be cotangent hyperbolic, lambda L, divided by lambda L. There you go. So that's the fin efficiency. Okay. Okay, good. Any questions so far? I cannot hear you. Is somebody speaking right now?
Yes, can you hear me now?
Somehow your voice is just not in. I don't know. Can you just speak louder, maybe, or maybe turn on up the microphone volume?
My mic. I'm sending you.
Okay, let me check. So you're sending me through the chat.
I will send you later.
I couldn't hear you. I'm sorry. Yeah, I can. Okay.
Can you
Yeah.
hear me now?
Yeah, I can hear you now.
Okay, I have a question.
Sure.
Last time we solved this second order differential equation based on that the end part of the fin is insulated. So
Yeah.
can we solve it for a fin that is open to the atmosphere, to the environment? For an infinite length fin
Yeah.
where the
Exactly.
end is open to the atmosphere or the environment.
Exactly. Excellent question. And who is speaking?
My name is Sifat Tanvir.
Who?
Sifat Tanvir.
Sifat. Okay. Great question, Sifat. So yeah, excellent. I mean, that you can call it case 3, right? Case 3. And you can have the following condition. So you can have like a finite, not very long L. And this is not insulated this time, but there is heat transfer, right? And you can actually tune or change your boundary condition too as Qx at L is equal to the Q by conduction.
Yes, Q by conduction.
At the fin end.
Fin end.
Exactly. That's an excellent excellent idea. Yeah. So you can say that I can just convert this Qx from the theta to Qx. I can write the expression and then write it equal to H times T minus TF. Exactly. And you would say that this is minus K. So let's do it. I think we have time, 8 minutes. Yeah, we can actually finish this. Yeah, that's an excellent point. K times dt over dx, so x is equal to L, is equal to H T minus TF at x is equal to L. Now, dt over dx, I had this expression here, right? Already. Here, this one. I'm going to plug in to this equation. T wall minus TF minus K. T wall minus TF over L. D theta over d psi is equal to H times, and T minus TF is nothing but theta times T wall minus TF from the definition of the theta, correct? And this is calculated that x psi is equal to 1. This is an estimate that psi is equal to 1, like the entire thing. And then you can see that T wall minus TF's cancel, right? And you get this nice boundary condition where you have d theta over d psi at psi is equal to 1 is equal to minus H L over K. And you can actually mute now if you don't have any other questions. H L over K theta at psi is equal to 1. And the theta over the psi is C1, oops, sorry, lambda L cosine hyperbolic lambda L psi plus C2 lambda L sine hyperbolic lambda L psi is equal to minus HL over K. Theta is C1 sine hyperbolic lambda L psi plus C2 cosine hyperbolic lambda L psi, right? And you plug in the psi is equal to 1 here. Right? And then C2 was 1 from the first boundary condition, right? From BC1. And you would get C1 lambda L cosine hyperbolic lambda L plus lambda L sine hyperbolic lambda L is equal to minus HL over K. C1 sine hyperbolic lambda L plus cosine hyperbolic lambda L. And you solve for C1, right? and you collect all the terms without the C1 on the right with the ones on the left. You can get C1 lambda L cosine hyperbolic lambda L plus HL over K sine hyperbolic lambda L, right? That's equal to minus lambda L sine hyperbolic lambda L plus HL over K cosine hyperbolic lambda L. There you go. So you can actually find the C1 pretty easily here. There you go. So that's your C1. Very complicated, but I mean, solvable, right?